Okay guys, last class I have discussed about the operation of digital frequency meter. Hello, hello, hello. Okay. So in the last class I have discussed about the operation of digital frequency meter, and in detail we discussed about how that control gate flip-flop is going to operate. So let us see if you look at this typical block diagram, how it looks. So gate controlled flip-flop block is here. So this one will consist of two back-to-back connected SR flip-flops, and we have seen how the main operation of this gate controlled flip-flop is going to operate. Stop operation, start operation, and next pulse operation. So this is here you can see the time-based selector is there, which will give you the user any to select any type of or range of time selection. From here you are getting the time-based selector signal that will be applied to both the top and bottom, start and stop AND gates, which are located on either side of the two back-to-back connected SR flip-flops in the gate controlled flip-flop. So this gate controlled flip-flop, what it is doing is, in overall, if you want to tell, it is simply giving you the time period for which these prescribed number of pulses will be allowed to enter through this main gate and given to the counter here. So that is a equivalent count of pulses proportional to the what you actually wanted to estimate as a number of cycles per second. In generally we can call it as a 1 second. 1 second is here. It may be 100 millisecond or 10 millisecond, whatever you are going to choose. Okay. So that's why this time-based selector, it is giving you the width of the pulse what you are going to apply at B input. A input is always there in the form of train of pulses as output of Schmitt trigger. So next thing, this digital frequency meter is not much sensitive to the measurement of higher frequency. So in order to avoid that problem, we'll take into account of other techniques other than the counting. So here what you are doing, you are simply, sorry. So here you are simply counting the pulses coming from the Schmitt trigger to the counter for the width of the input pulse what you applied at B. So it is based on the counting the pulses in order to measure the frequency. But it is not sensitive to measure the high frequency. Okay. So high frequency means the number of cycles per second. So in 1 second, the number of cycles which are crossing this gate are large in number. So that's what we are telling. The counter will become not much capable, or you can say sensitive enough to count all those pulses which will increase drastically at higher frequencies. Are you getting this point? This is the main key point here. So in one sentence, we can just tell it as our DFM is not sensitive enough to the measurement of high frequency. So for that, we can go for adopting different techniques here. Like the first one is the pre-scaling. So in pre-scaling, what we'll do, high frequency signal is divided by some integral numbers like 2, 4, 6, something like that, by high speed divider circuits. Divider circuit means last block diagram notidirla. Crystal oscillator will go on generating 1 second, 100 microsecond, 50 microsecond, like that. Different time scales of the time-based selector will generate by using divided by 10 decade counters. ಸೊ ಅದನ್ನೇ ಇಲ್ಲಿ ಯೂಸ್ ಮಾಡ್ತಾರೆ. ಸೊ ದೇ ಆರ್ ಯೂಸಿಂಗ್ ದ ಸೇಮ್ ಕಾನ್ಸೆಪ್ಟ್ ಹಿಯರ್ in dividing your high frequency signal successively by these numbers. First they will divide it by 2, next whatever they will get divided by 4, next whatever output you will get they will divide it by 6, like that. That is called pre-scaling. Same thing we are doing there. Crystal oscillator use ಮಾಡಿಬಿಟ್ಟು ಬೇರೆ ಬೇರೆ ಟೈಮ್ ಸ್ಕೇಲ್ ಜನರೇಟ್ ಮಾಡಲಾಗುತ್ತಲ್ಲ ಟೈಮ್ ಬೇಸ್ ಎಲೆಕ್ಟ್ರಿಕ್ ಯೂಸಿಂಗ್ ಡಿವೈಡ್ ಬೈ 10 ಡಿಕೆಡ್ ಕೌಂಟರ್. It is similar to pre-scaling itself. ಅಲ್ಲಿ ಕ್ರಿಸ್ಟಲ್ ಆಸಿಲೇಟರ್ ಇರ್ತೈತಿ, ಬಟ್ ನಾವಿಲ್ಲಿ ಹೈ ಫ್ರೀಕ್ವೆನ್ಸಿ ಸಿಗ್ನಲ್ ಯೂಸ್ ಮಾಡ್ತೀವಿ ಅಷ್ಟೇ. ಹೈ ಫ್ರೀಕ್ವೆನ್ಸಿ ಸಿಗ್ನಲ್ ನಾವು ಸಕ್ಸೆಸಿವ್ಲಿ ಡಿವೈಡ್ ಬೈ 2, ನೆಕ್ಸ್ಟ್ ಡಿವೈಡ್ ಬೈ 4, ನೆಕ್ಸ್ಟ್ ಡಿವೈಡ್ ಬೈ 6 ಮಾಡ್ಕೊತ ಹೋಗ್ತೀವಿ. And we know that if you divide anything by 2, its value will be successively or proportionally go on decreasing. Because it is high frequency measurement, we have to proportionally, it's something like we are alternating it proportionally, in other words, if you want to tell, for the purpose of measurement. That's all. Next one is a heterodyne counter. So where this HF signal is reduced within the frequency range, reduce ಆಗಿ ಮಾಡತ್ತೇವೆ. So we'll let DFM will be there. Digital frequency meter ಅದು ಅಲ್ಲೇ ಇರ್ತೈತೆ. Its inability ಏನು ಗೊತ್ತಾಗೈತೆ, it cannot measure high frequency. But what we are doing now, we are dealing with high frequency signal. High frequency signal ಅನ್ನು ನಾವು ಅದರ frequency range reduce ಮಾಡಲಾಗ್ತೇವೆ. That reduced one we will be giving again back to the DFM. That's all. DFM will be there. It will be doing its duty as it is. Only thing is that now, as it has the limitation that it is insensitive to measure the high frequency, simply what we are doing, we are dealing with the high frequency signal, converting it to the suitable some reduced frequency range. So in this heterodyne counter, we are trying to reduce that one to the lower frequency range by heterodyne methods like modulation method. So you might have seen that in the superheterodyne receiver that you might have learned in the basic electronics. There what you are doing, you are mixing the high frequency carrier signal with the low frequency modulating signal. Isn't it? Can anyone respond to me? This is important here. Yes. Is it correct what I am telling you? Have you came across this superheterodyne receiver in the basic electronics? Can anyone tell me? Can anyone respond to me here? Yes. So here, there what we are doing, we are mixing high frequency carrier signal with the low frequency modulating signal. Thereby, the output signal what we are getting is a mixed one, so reduced in some frequency range. So next one we can see transfer oscillator. So where harmonic low frequency continuous wave oscillator, you can see here long form here, harmonic low frequency continuous wave oscillator. This kind of method or setup is used to mix up unknown high frequency signal to produce low frequency oscillator frequency. Automatic divider where high frequency signal is reduced by some factor. So here you can see, so that is one difference between the pre-scaling and automatic divider. In pre-scaling, we are trying to scale it by some proportions like 2, 4, 6 successively. But whereas in automatic divider, we are already knowing that by what proportion or factor it should be reduced. So it should be reduced by 100:1. 100:1. Automatically tuned circuit will be used. So these are the different techniques which are adopted in extending high frequency measurement ability of the digital frequency meter. Hello? Hello? So next one we can see today, today's main discussion is digital measurement of time. Its operating principle lies in similarity with the digital frequency meter only, how we have measured the frequency there. Now you can see here, it is a measurement of time. We all know that the relationship between the frequency and the time. Frequency, how you defined? It is the number of cycles in 1 second that are passing. So whereas time, if you take the frequency reciprocal, it is going to be number of cycles per 1 second you have told. So it is 1 second per number of cycles. So that doesn't mean any here. But reciprocal of f will take it as a t here. So what we are doing, we are trying to adopt the same thing here. So here the operating principle of the time is actually based on, so whether you did it or not, I don't know, on the CRO or oscilloscope screen. So if I will give you, if I'll show you one waveform, how you can measure the time period there for one waveform? Can anyone tell me? How you measure the time period of the waveform, given waveform? It is as good as we'll consider one reference point, starting reference point, and same ending reference point we will consider for the one period. That is going to be the measurement of time. So here also, as it now requires two reference points here, one reference point must tell us from where we have to start on the waveform, and second reference point must tell us where we support to stop the measurement of time. So same thing will be done with the help of two inputs here. That's why we need two inputs here. One input is going to one input signal that is giving you the starting point, and another second input signal will be giving you the stop signal. Now both will be given as two inputs of the gate control flip-flop. So as long as both are on, these pulses will be applied to the main gate, counted and displayed. That's all. So in between the start point and stop point, whatever the pulses are passed with the help of this main gate and gate control flip-flop will be counted by decimal counter and displayed. That is nothing but equivalent to the counted pulses are equivalent to the measurement of the time period. Now if you look at this, the block diagram, which is very much clearly given here, setup will be remaining same. Once again, you can see it is similar to the time-based selector setup. Once again, 1 megahertz crystal oscillator is converted into a 10 of pulses, and its frequency, 1 megahertz frequency, is successively divided by 10, will get 10 to the power 5 hertz. Then again it will be divided by 10, you will get 10 to the power 4. Again it will be divided by 10, you will get 10 to the power 3. So here for the simplicity of diagram and explanation, we have just given output of this divided by 10 frequency only as input to the this main gate. So other two input is coming from the gate control flip-flop. So here the user will be given a choice to select any of the time period he want to measure, and another input is coming as output of the gate control flip-flop. So what gate control flip-flop it is doing? For the period duration, you can see here. So input one signal is applying here through attenuator and amplifier. Attenuator, what it will do? If your signal 1 is not in the visible proximity on the screen, then it will be reduced in amplitude proportionally so that we can view on the screen comfortably for the measurement of time period. Otherwise, without seeing the waveform on the screen, we cannot measure it. Then it will be given as input is mid trigger, which will be converted into train of pulses. And here we are getting one of the input to the gate control flip-flop. Another input to the stop gate. So how long these pulses will be applied to the gate control flip-flop? as long as you will get the stop point or stop input signal or stop that reference point will came across. That will be detected by this one, and here it will be applied as stop gate to the gate control. So as soon as we will get the stop pulse, before that all the pulses will be applied to this decimal counter counted. So once you will apply the stop pulse to the gate control flip-flop, then it will be stop. It will be disabling its output. So main gate will be disabled. No more pulses will be applied to the decimal counter. Whatever it is counted, it will be displayed. That is proportional to the measurement of the time. Okay. Are you understanding this one? So after digital frequency meter, this is another very important device we are covering today. So this digital time period, let us see. So digital frequency meter, one limitation we have seen just now, that it is unable to measure high frequency. That's why we gone for studying different techniques, how we can extend its ability to measure the high frequencies that you have seen in the previous some slides. Similarly, this digital time meter has got one drawback here. So this is the diagram actually got it from the notes here, similar to this only. So you can practice it at home and try to see the notes also. Operation is given there. You can easily understand it. Not much difficult. But the one important limitation of this digital time meter is this one. Suppose if I want my digital time meter to measure 60 hertz, sorry, 16, uh, we will go reverse. Okay. Suppose if I want my digital time meter to measure 16.6673 millisecond. It will depend on its resolution, how many decimal point it is able to display on the screen. It depends on the resolution of the DTM. But if you take the reciprocal of this one, you can see how much you are getting. It is not 60 hertz, because we know the relationship between frequency and time, both are reciprocally related, inversely related. So we can see 60 hertz and 59.9977. You take the difference of these to get the error. So how to minimize this error and improve the accuracy? Means what is happening here is that, so stop pulse we are applying in advance. Means we are not letting the DTM to count final few pulses. Means our DTM means we are restricting our DTM by sending stop pulse in advance by this much of value error. If we also count those pulses, extra pulses, means what we have to do, we have to delay this stop signal by using this one. That is called multiple period average mode operation. You can see here, we are trying to apply the stop pulse. You can see here, start pulse itself I have taken as input and applied through 5 decade counters. So this signal, while going through these 5 decade counters, will be undergoing some delay. That is known as a multiple period delay, multiple period triggering, and then it will be coming. So this much delay is sufficient to count also those extra pulses, whatever the pulses we lost, so that we can cope up with this much of error, and we'll get nearly 60 hertz. That technique is known as a multiple period average mode operation, MPAM technique. Hope you are understanding this one. If you want, I can repeat now itself. So this is a very important concept in DTM, an important device we are learning today. Okay, good. I hope you understood this one. Next one, how to measure. So we have seen so far how to measure frequency, how to measure time period. Also we have seen their limitations, and also we have studied how to minimize their limitations and extend their performance. Next one, we will see how to measure multiple frequencies. It is similar to this
Excuse me, sir.
MTM technique.
Excuse me, sir.
So here,
Sir,
yes,
sir, labs
pardon.
sir sent the link of labs sir and told to compulsory join sir.
Hello, your voice is breaking.
Sir sent the lab link sir
Ah.
and told compulsory join ಇದು must join sir. So can you leave this class?
I will let me give another 5 minutes. I will let me wind up. Okay.
After that they sent link at 2:30 only sir.
No, you can tell them that class is happening. After the class, they have to take the lab.
We told sir but they are not arguing sir. They are
Okay, let
too
me
much.
wind up. Let me wind up. 5 minutes you can give me.
Okay sir.
Okay.
Okay, sir.
Next one, we will see how to measure multiple frequencies. This is similar to this one only. We are applying low frequency here as one of the input signal that is coming here as a gate control signal. High frequency signal will be given as a main gate signal. So idea here is that these things already I have explained in MPM technique. If you want, you can also refer to the notes for the full description. So I want all of you to come with reading all of these things before attending my next class. So here idea is that we are going to measure how many high frequency cycles or signals are going to pass in one low frequency cycle. Let me repeat here. How many F2 signals, high frequency signals? So, how many F2 high frequency signals are passing through the low frequency F1 signals? That will be counted and displayed. That's all. Next one is a universal counter that is able to measure frequency, period, time interval, ratio of time periods, ratio of frequencies, extension of standard control voltage, etc. Okay. So I suggest you to go through the notes. So today I will. So all of you come up with reading these things. Next class, if you want, I can repeat some of the concepts before going for the next section. So next section we are going to discuss about bridges.